All right, good morning, everyone, and welcome to this presentation of the Alta webinar series but on drawdown of soil oh my gosh, I can't talk. We're gonna have to re-record this introduction for the online version. But for this presentation of the drawdown of soil phosphorus by crop removal, a meta-analysis of fields with halted fertilization. And I'm going to just make this comment. I've never heard the term halted fertilization, but I liked it a lot. So I'm hoping you define that right off the bat. Our presenter today is Dr. Luke Gatiboni. I probably did not say that right. I apologize. From Soil Fertility Extension Specialist at North Carolina State University. And with that, Luke, I'm going to hand it off to you. And we'll see. I'll stop sharing. And hopefully you can start sharing.
Okay, thank you, Corey. Thank you very much, first of all, for the invitation, and thank you everyone for attending this webinar. Let me see if I can share my screen right now. And are you seeing that?
We're seeing your screen perfect.
Okay. So this conversation will be about drawdown of soil phosphorus. So we know that we have some situations where we have accumulation of phosphorus over the time, and so we have a few options to reduce the phosphorus, the available phosphorus in the soil. And one of these options would be just to crop the soil without fertilization and see how and try to remove this phosphorus from the soil. And so this study was made by many hands. We have Amy Schauber, Nicole Fiorellino, Diana Osmond, and Laurin Mosesso. And we work in the last, I think, 1.5 years on this project, trying to gather information about drawdown studies and try to put all this information together in a easy way to see it. And so this is the presentation that we will make today, and I'm very glad that you are here for that. And so we'll talk about the accumulation, the phosphorus accumulating in the soil, and we can call this legacy phosphorus. This is one of the names that is out there. It's the phosphorus that we are applying above the amount that our crops are exporting and the losses. We also can call this residual phosphorus. We can call this available phosphorus, and I'm seeing Andrew Martinot in this call, and we have a very nice paper from them for his group talking about the differences in these different concepts that we have out there. And so I'm using here legacy phosphorus and residual phosphorus and available phosphorus as the same thing. And so when we think about the accumulation of available phosphorus, the way that I see this occurring over the time, I'm imagining a field that we have, for example, a low availability of phosphorus, and we need to increase the phosphorus availability. And so we'll start to do fertilization. We will add phosphorus in organic forms or mineral fertilizers. And every time that we add fertilizer, we will increase a little bit the amount of available phosphorus in the soil. And so we are moving from this level A to a level B. And if you put a crop, and this crop will remove part of this phosphorus, we will have the phosphorus reducing a little bit because the phosphorus exports. And so I will do a new fertilization. I will bump a little bit more the phosphorus. And if I'm doing this over the time, over and over again, what we can expect is that the phosphorus will increase it. Will build up in the soil just because phosphorus, it's not easy to remove from the system. We have phosphorus fixation, or we have absorption. And so we expect anytime that we are doing a management where we apply more phosphorus than removal, that we will have over the time the increase of this phosphorus. And so this would be the legacy phosphorus or the residual phosphorus. So one example of this is North Carolina. North Carolina, these are the average soil test P in the early 2000s. And you can see here that we have some counties that in average, this is just the average of the some soil tests. We have some regions that we have a lot of phosphorus, very high phosphorus status. We have some other regions in yellow where, and at that time we had high phosphorus, and the green counties with phosphorus below the critical soil test value. And the reason that we have these differences is because this region, the eastern North Carolina, is where we have more agriculture, and so we are adding more phosphorus. In this region, we also had historically tobacco production, and so we applied more phosphorus for that crop. And also because in this region, we have a lot of animal production, and so we have manures that we will apply in the soil. But when you look at the situation that we have in the last 5 years, these are some results from 2020, and you can see that we are accumulating. We have more and more counties in North Carolina that we have in average very high phosphorus. And so this is what occurs when we are applying phosphorus above the crop exports and the losses to the environment. These are, again, some average numbers for North Carolina. These numbers are from our state lab, North Carolina Department of Agriculture. We have a very nice soil testing lab that is free of charge for our farmers. And we can see that for 2019 and 2020, more than 85% of the samples for grain fields we did not apply. We did not need to apply phosphorus in those fields because they were above the critical soil test value. And for cotton, we had 87% of the fields that were tested, of course, above the critical level. Peanuts, 96%, pasture and hay fields, 73%. And so it just shows that this problem with accumulation of phosphorus is common, at least it's common in North Carolina. And so when you think again about this accumulation of phosphorus, what would be the options that we have? We don't have many options, but the lowest hanging fruit would be just crop that soil that we have very high fertility without applying fertilizer. And so we will start a drawdown management of those fields. And so when we think about how would work the drawdown, I would just keep cropping that soil, and I expect that we have some removal of phosphorus. And so after one crop season, I remove a part of this. The next crop season, I will remove more phosphorus, and every time that I'm cropping that soil again, I expect that this field will reduce the amount of available phosphorus because I'm not replenishing the amount that I'm exporting by crops. And the question is, how much time is needed to reduce the soil phosphorus to a certain level? For example, if I want to reduce 50% of that phosphorus, available phosphorus, how much time do I need? And so we have some very nice data from North Carolina. I love this paper from Dr. Kemper. It's from 1999. And he had 14 years in 3 different sites in North Carolina. He cropped with soybean and corn, a rotation of soybean corn in 3 different soil types. And he saw that in a soil, a Lynchburg soil, he was able to reduce about 2.8 to 3 ppm per year in this crop rotation using corn and soybean. In this other soil that started with 55 ppms of Mehlich 1, the reduction was about 2 ppm per year, and in a Davidson soil, a half ppm per year. And what he saw is that it took about 10 years to reduce 50% in this soil, 12 years to reduce 50% of phosphorus in this second soil, and about 18 years would be needed to reducing 50% in this Lynchburg soil. And so it varies, at least in North Carolina, in this example, it varies depending on the soil type and the characteristics, and also where you started in terms of initial soil test P in this drawdown study. But the motivation for our study was, we have this nice publication from North Carolina, and we have another very nice publication from Nicole Fiorellin and from Maryland. And when you compare and they work with haylage, and when you compare the slope of these curves in North Carolina and in Maryland, we saw that they are very similar, regardless that one is working with corn and soybean, the other one is working with a different crop system. And in these two situations, it was exactly the same percentage of reduction. From 3 to 5% per year was the reduction in the soil phosphorus when they during the drawdown time of these different studies. And so when you look at these two papers, we thought, is this a trend? Is this something that is just because these two regions are close by and the soil are maybe similar? And so we decided to try to see other papers, other publications, and compare them and see if they were similar in terms of drawdown. And so the objective of our group when we start to work was to gather different studies with phosphorus drawdown and doing a meta-analysis to verify if they have a similar drawdown pattern. And so before we go to our conversation about the results, I would just take some minutes just to talk very quickly about the meta-analysis and how it would work. So a meta-analysis is the use of statistical methods to summarize the results of a group of studies with similar objectives or treatments. It means it's just a way to try to get a bunch of information and summarize this information in a way that is easy to see the results, the average results. And so I always use one example for that. And one example of a meta-analysis that I like is from this publication from Abelos in 2022. And these authors, they compare the efficacy of different nitrogen enhancers or inhibitors. And what they did, they gathered a bunch of papers that were working with different nitrogen inhibitors, DCD, NBPT, DMPP. And the question was, are these inhibitors working in general when we look at all the information that we have published? And so they got a bunch of papers and they did this meta-analysis. And I will show you how we read the information in this graph. First of all, we have this graph that is summarizing all the information. And we can see here the last number here is the number of studies. And the first number here that is close by to each information is the number of pairs, because they were comparing the efficacy of applying any of these enhancers when compared with applying only nitrogen without the enhancers. And so they are compared the pairs. The control is only nitrogen and the other treatment is with one of these enhancers. And so the comparison that they did here, the yield response, they set for the only nitrogen as 0. And when they apply nitrogen plus the enhancer, they calculate the average increase in yield. And we have the mean, and this mean is the mean of 106 pairs of comparison of these different papers, very different information in different situations, but this is the great average of everything. And what they did, and this is when the meta-analysis works, is they did a they calculate the confidence interval based on a resampling test. And we usually use bootstrap. And in the bootstrap, we will do many simulations using that numbers. And it's common to do 2,000 simulations, 5,000 simulations. In the study that I show you today, we did 5,000 simulations in each data set. And so with these simulations, we can calculate the confidence interval. And so we can see here the confidence interval, and this confidence interval is telling that 95% of the time, your observation will be from the resampling test, it will be within that range. And so just looking at the results of this study, for example, the conclusion that they got, looking at all inhibitors, that yes, the inhibitors increasing about 7% the yield, and they can say that the inhibitors increase the yield based on this test. But when they look at DMPP, one of the enhancers, the DMPP in the average increase only 2%. When you look at the range of the confidence interval, the confidence interval is overlapping the control treatment. It means that we cannot say that the DMPP can increase yield because it's within the confidence interval of both observations. And some other things like NBPT, this one is better than the MPP because they are different and we don't have the confidence interval overlapping. And these other two products, NBPT and DCD, they cannot say that they are different because, again, we have overlapping in the confidence interval. And so this is the way that we use this meta-analysis to compare these big things. Again, this is just a big average. It's just to have an overview about many different studies, 27 different papers, 106 different treatment comparisons. And so we have a bunch of different things there. But as I said, it's just an average. And so the meta-analysis shows trends. And the quality of this meta-analysis, the meta-analysis that we see, it depends on the data sets that we select. For example, if you have a huge number of observations, we have more confidence on that meta-analysis. And also it depends on the data sets that the user choose, because we need to compare apples with apples. If you get papers that are so different in terms of conditions, we can do the meta-analysis. We'll have a number, but that number maybe doesn't make sense when thinking in terms of the agronomic response. And so meta-analysis is as good as the studies that you can select, as more similar they are, and also then depends on the number of observations. Okay, and so going back to our drawdown, phosphorus drawdown study, we started just with this observation of two papers that were very similar, and we decided to see if you could see this similarity in other studies that were working with drawdown. And so the objective was to determine the average yearly reduction of available phosphorus when the fertilization was stopped, and determine what factors affect most the drawdown rate, what make different drawdown percentages or rates in different studies. And so we need to have some criteria to select the papers. And remember that we need to try to compare apples with apples. And so we put some rules to select papers for this study. The first rule was, of course, that we need at least one treatment with a phosphorus drawdown, years without phosphorus application, and with crop removal. Another thing that we put to have at least 3 years of drawdown, because we have a bunch of papers that we just stopped the fertilization, and we measured the phosphorus after 1 year or after 2 years. And we can see we have some variation in the soil testing when we are considering very short period of times. And so we decide to have at least, to consider only papers that we had at least before and after 3 years without fertilization, to be a little bit more safe in terms of really seeing the amount of phosphorus that were decreasing without phosphorus fertilization and cropping. And the next thing that we decide, we consider only those papers where the soil testing phosphorus was measured by Mehlich 1, Mehlich 3, Bray, or Olsen. We had many other papers that were measuring other methods that we have less capability to convert the numbers from one method to other. We'll talk about this in the next slides. But when you look at these papers, we found that at least 27 publications that we had the drawdown curves. But when we set those other rules to have at least 3 years without fertilization, with soil testing phosphorus before and after at least 3 years, and when we set only Mehlich 1, Mehlich 3, Bray, and Olsen, the number of publications that we were able to use dropped to 14 publications. And in these 14 publications, we had 56 drawdown sites or treatments that we were able to work with. And so this is the list of the publications. The publications are varying from 1979 to 2019, I think. And most of these publications are from the US, but we have some sites that were considered that are from studies in Canada, one in France, and 2 treatments in a study in the Northern Ireland. So what we did after we selected these different publications, we need to extract the data. The first thing that we record, of course, is the soil test method that they use to measure the phosphorus. The second one was to extract this soil test P results. And you can imagine that in these different papers, we had different units, and we did the conversions, and you convert our numbers to milligrams per kilo using assumed density 1.18 when we didn't have the density informed in the papers. And I will show you how we extract all this data in the next slide. Another thing that we did is to record the crop rotation that they use. And again, we can imagine that in these different treatments, in different papers, we had a lot of different things that were used as were cropped in these different publications. But we made groups, big groups, thinking about how these plants would perform in terms of amount of phosphorus that would be exported. For example, grain, just a grain rotation where we grow grain crops during the summer. We had another situation where we consider double crop grain when we have at least one winter where we had some exports of phosphorus, for example, wheat. Haylage, that you can expect that we have more exports because we are exporting a lot of biomass from the field, and we are exporting phosphorus, and pastures. And so in these 4 big groups, we put out the information, the 56 sites. Another thing that we were able to extract as a metadata from these different publications were the soil texture, because we can imagine that when we have a sandy soil, we have less interaction, less phosphorus fixation, and maybe it's easier to export phosphorus than in a fine textured soil, a clay soil. And so we got the information that we have in the papers, and we were able to make 3 big groups: clay soils, loamy soils, and sandy soils. And we use the triangle, the texture triangle, to separating these different classes. The most important or one of the most important information would be the phosphorus exports or the crop yield in these different publications. But unfortunately, we have some of these papers, or many of them, they were just informing about the soil analysis, and they were just informing we did this rotation, but we don't have, was not a paper about crop yield. And so unfortunately we didn't have in our papers this information, so we were not able to use crop yield, phosphorus export, or any other information like CEC, soil pH, because some of these papers are informing that, many of those are not informing. If you drop all the papers that are not informing phosphorus export, probably we had less than a handful papers, and we would not be able to do meta-analysis with very few information. So this is the hard decisions. We didn't use phosphorus export because it didn't have. Okay, but all this information that I'm showing, soil phosphorus method, crop rotation, soil texture, and soil test P were the information that we were able to use in our study. To extract this data, you can imagine we have some papers from 1979, only a PDF of these papers. We use an online tool, web plot digitizer. It's an online tool that we can extract data. You upload your PDF. This is a PDF of one of our studies, and you use your mouse just to set the axis and the scale of each axis, and after you can click on the data, and you have a zoom here that you can try to hit the target, to aim the target. And after you click on now your data points, you can export the data. Of course, it's not perfect. It depends on how good are you looking at this and how good is the quality of your PDF. But it's kind of, you can extract with a good confidence at least the close to the numbers that are in the publication. Of course, some of those publications that we used, the information were in tables, and so we had the numbers ready to go in the tables. But for those ones that we need to extract from the graphs, of course, the information is approximate. It's not exactly the information, original information. This is the data after we extracted this data, and we converted everything to milligrams per kilo. And you can see a bunch of curves with Olsen, Bray, Mehlich 1, and Mehlich 3. And one thing that we need to do in this data set was just to modeling the drawdown, how the phosphorus were changing over time. For example, one of our papers, they had, in the first 4 years, they had analysis every year, but after they just jumped 3 years and had analysis in the year 8. And so we didn't have 3 years of data here. And so what we did to have enough data for this analysis, we rebuilt this model, these equations, and we use the modeling number instead of the originals to do our analysis. And so we were able to get numbers for each year of this drawdown study. And this is how the data looks like for all site years that we were able to use. And that's a bunch of data points, and it's kind of a massive graph. But let's see what we can extract from this massive data. One thing that we did, of course, is that remember that for most of this data, we use that web tool to select the data to extract the data directly from a graph. And so, of course, that we have an error there. And when we are in the end of a drawdown curve, the differences are very, very small. And so we decided to just remove the last points when the difference was less than 0.1 milligrams per kilo, just because we cannot say that it was just when we extract the data that we saw that small difference, or it's something that just occurred. And just to play safe, we remove the years where the difference in the end of the drawdown, when the years were very similar, the phosphorus concentration was very similar. And of course, we lost a lot of years. One of our studies was 26 years of drawdown, but we removed 10 years of that data because they are just a flat curve. This is just, in the end, we had a very big Excel spreadsheet with all this data. And let's see how we use that data for our analysis. The question that we had after we extract all the data, we had these 4 different things: the initial phosphorus in the soil, the method, the soil testing method, Mehlich 1, 3, Olsen, and Bray. But we had the crop rotation in those 4 big groups, and the soil texture in those 3 different groups. And the question is, which of these one is the most important factor when you see the drawdown, especially the slope? When you what make this one different of this one? Is the initial phosphorus that is high and make it drops very quickly, or is because this set of data here is by Mehlich 3, or it's because this is in a sandy soil, or so on? And so this is the first question that we had. And as we didn't have many data points, only 56 drawdown sites, we cannot answer to do the analysis separating all these 4 parameters, because we would end up with just 3 or 4 observations for each of these classes. And so we need to choose the best one to use all the information using the best parameter. And so we need to choose one of them because we only have 56 sites to use. And so the first thing that we did, we tried to see what's the most important parameter. Is initial phosphorus, is the method that they use, is the crop rotation, or soil texture. For looking at what's the most important parameter, we did a bootstrap forest of decision trees. Decision trees is when we try to split your data set, and you try to see what's the best split in different groups. And we did all this analysis in JUMP. It's a software. And what we did, we look at the contribution to the sum of squares of each of these parameters when we did these 1,000 trees in this simulation. And what do you see in the first year of the drawdown, second year up to the year 15, that always the initial soil test P was the most important factor. In average, 80% of the sum of squares was related to the initial soil test P. It means that the soils that start with a very high P, they decrease in a quick way, in a quick amount of drawdown, a quick rate, than when you compare with soils with low initial soil test P. And the second thing was the method, and it was in average 10%, and after we had the crop 8%, and the texture was the less important factor. And so 80% of the sum of squares in average was related to the initial soil P. And so because we didn't have a lot of sites, if you need to choose one of these to be our big parameter to look at, would be initial phosphorus, where we started in terms of concentration, where we start our drawdown. And so we chose this one, but we had different soil testing methods. We had Mehlich 1, Mehlich 3, Bray, and Olsen. And so before you compare all these things, we need to transform the different methods in equivalents of one of these methods. And we use the same approach as the IPNI did, according to the Fertilizer Institute. They use to, when they do those soil test levels in North America, this publication, I think we had one in 2015 and another one in 2020. It's the last two ones. And they have in this website the conversion factors. IPNI, they convert everything to Bray equivalent, and we decided here to convert everything to Mehlich 3 equivalent because we are in the East Coast, and we decided Mehlich is the way that we use it to do, and we had many sites from the East Coast, and so we decided to change to put all in equivalent to Mehlich 3. And so we get these availability classes, the equivalences from the IPNI, and we build these equivalences, these equations, and we were able to transform Olsen, Bray, and Mehlich 1 in equivalent Mehlich 3 by ICP. And so these were the way that we did. And so we converted everything to Mehlich 3. The second thing that we did, okay, we have all the data in Mehlich 3 now. And we know that the most important thing is that the soils with high phosphorus, it seems that they are performing different from the soils with low phosphorus. How many classes we need to separate all this data, these sites? What is high phosphorus? What is low phosphorus? Well, we could use just like an agronomic view, like, okay, look at the recommendations that we have for different states that are using Mehlich 3 and decide when do we have less than, I don't know, 50 ppms, we consider this medium. When it's 50 to 100, it's high, something like that. We decide to do a different approach. We look at this data. We put all this data in a partition analysis, and we did a decision tree. And we, in this analysis, we look at what would be the best split to get more homogeneous groups. And we did this analysis, and the best split was to form 4 different groups, okay? And these 4 different groups were, and it was decided by a decision tree, from 6 to 29 milligrams per kilo of initial soil test P was one group that was more homogeneous. The second group that I called medium is not medium, agronomic medium, is just medium in our scale, from 30 to 66. The third group that I consider, I call this high, is from 77 to 115, and the very high from 116 to 261. And this is all the data range that we had from 6 to 261. Why only 4 groups? Well, in the decision tree, we try to reduce these to 3 groups instead of 4. And when I did decision tree for 3 groups, the R-squared dropped 20%. And okay, what if we increase instead of 4, let's put 5 groups. When I increase from 4 to 5 groups, my decision tree, the R-squared, increased less than 1%. And so if you drop to 3, we lost a lot of information. If you increase to 5, doesn't matter. You are not increasing the quality of analysis. And so it seems that these 4 groups were the best split, and we decided to use these ones for our meta-analysis. So we split all our data transformed in Mehlich 3 equivalent in these 4 different groups, and we did the meta-analysis. We just now we start the meta-analysis, the last step of our study. And so for each year, in each one of these 4 groups, we did a bootstrapping with 5,000 resampling. and we calculated the average by resampling and the confidence interval, 95% confidence interval for these different years and different groups based on the initial Mehlich tree equivalent. And so we did all these things to have this graph. And this is the graph that represents these 4 different groups of Mehlich equivalent. And you can see in the y-axis Mehlich tree equivalent in milligrams per kilo. Here we have the drawdown year, and you can see that the maximum we had 15 years, because we need to drop some of those years. We can see the small number close to every of these averages are the number of observations that we had. And you can see for some of them, we had 14 observations, and we dropped to 9 in the end, because we had less observations, less studies with 15 years of drawdown. Some studies we start with 17 and we end up with only 3 observations. And you can imagine that when you have only 3 observations, it's an average, but it's not safe. But that's the problem with drawdown studies. We don't have a lot of studies out there that are just cropping for 20 years, 15 years without fertilization. It's very hard to have these long-term trials. So this is the results. The interesting thing that we were able to adjust an exponential decay model for all these curves, and you can see the R-square were very good for all of them. And this model were significant for each of these curves. You can see by the confidence interval that for most of these data, these 4 groups were different. The only time that they were not different is these 2 here and these 2, because we have the overlapping of the confidence interval, as we talked in our example about nitrogen. But in average, these 4 groups were completely different in terms of drawdown. For the first group of low phosphorus, initial low phosphorus, we dropped from 19 ppm to 8 ppm after 10 years of drawdown. For the second group, we decreased from 48 to 27 ppm. The first one, the drop was about, in the end, we had remaining about 40% of the initial phosphorus. In this one, we had about 50%, 55% of the initial phosphorus. The third group dropped from 95 to 46, and it was about 49% of the initial phosphorus remaining after 10 years. And for those sites that started with very high P, it drops from 193 to 124. After 10 years, we still had about 65% of the initial phosphorus. Of course, because you have a lot of phosphorus here, it's hard to export that phosphorus. And after 10 years, we still have a lot of phosphorus. And again, this is just an average of all those studies. Okay, and what we are interested in this is more in the slope of these different curves. But when we have this exponential decay model, we can calculate the half-life, how much time we need to drop exactly 50%. And we can just use this equation, and we calculate for our 4 different groups. In the first group, we need about 80 years to reduce 50% of the phosphorus, because we start with low phosphorus, and so in 80 years, we'll reduce 50% of that initial phosphorus. For the second and third group, we had about 10 years to reduce 50%, and for that group that we start with very high phosphorus, we need about 16 years to reduce in 50% the initial phosphorus when we were using the drawdown. We also did all the meta-analysis and the bootstrapping using the difference between each year. And you can see here for the drawdown rate in milligrams per kilo per year. In the first group, we started with a reduction of 1.7 ppm in the first year, and the 10th year, it drops to 0.7 ppms. For the second group, 3.5 in the first year. For the other group, 6.5 in the first year. And for the very high phosphorus, 13 ppms per year in the first year was the drop. This is for each of these years. We did for the first 5 years, from the year 6 to 10th, and from the year above the 10th year. And you can see here the average numbers for the different groups. And this would be the average drop per year that you would see in these different initial Mehlich tree equivalent groups. Or if you want a big average of everything, this would be the big averages. For soils starting with low phosphorus, the average drop will be about 1.2 milligrams per kilo per year. In the medium phosphorus, it would be about 2.93 milligrams per kilo per year during the drawdown, the yearly reduction of phosphorus. In the third group, from 67 to 115 milligrams per kilo of initial phosphorus, or what we call high phosphorus, initial phosphorus, the drop would be about 5 milligrams per kilo. And if you start with a very high phosphorus, up to 261, the expected, the modeled yearly reduction would be 8.5 milligrams per kilo. Of course, this is big averages, as all the meta-analysis is just an average, just general trends. But based on that modeling, we could use the equations that we have. And if you replace, if you have, instead of 6, you have your soil with 15, you could put 15 over here. And if you use this equation, probably you have a good estimation of your drawdown. And here would be the number of years of drawdown. For example, if you start with 15 ppms, Mehlich tree equivalent, we'll put 15 over here. If you want to know how much will be the phosphorus after 12 years of drawdown, we'll put 12 over here, and we'll solve the equation. We'll have an estimation of your phosphorus in the soil after 12 years. And we have one equation for each of these groups of initial soil test phosphorus. Remember, this is all Mehlich tree equivalent. We transformed everything. And remember that this is big averages of many averages. And so we need to be very careful with these numbers. They are good trends. I think they can show us something. But of course, we need to use these carefully, this type of numbers. And so the conclusions that we have, the soil test phosphorus at the beginning of the drawdown management is the most important factor affecting the drawdown rate. When we consider, of course, only the initial phosphorus, the method, the texture, and the crop, the information that we have. Soils with very high initial soil test phosphorus, the average reduction was about 8.6 milligrams per kilo per year. This is the big average, or you could use this equation. Soil with initial high soil test phosphorus, the reduction was about 5.1 milligrams per kilo per year. And we also have an equation that could use for that. Soils with medium initial soil test phosphorus, the reduction was about 2.9 milligrams per kilo per year. And if you start with low initial soil test phosphorus, below 29 Mehlich tree equivalent, the average reduction would be about 1.2 milligrams per kilo per year. And for soils with Mehlich tree equivalent below 261, this is our range, the highest one. In general, it's possible to draw down 50% of phosphorus in about 8 to 16 years without fertilization. Again, big averages, only trends, and numbers to be used very carefully, but still numbers, interesting numbers to have, to predict, to have an idea how fast or slow would be to reduce phosphorus accumulated in the soil. So this is what we did, and I will happy to answer questions if I can. And so, Corey, I get back to you.
Yeah, thanks. So sorry, I was just shifting over to my PowerPoint real fast, which hopefully you guys are now seeing. Yeah, looks correct. So before we move into questions, I did want to share that Alta has a summer in-person workshop, August 19th and 20th in Bloomington, Illinois. You can use the QR code on the screen to learn more or register. There is going to be some great presentations. We have some FRST groups there. NAPT will be there in addition to some conversations from other labs. And so I'm really looking forward to that. One of our event sponsors is going to be Precision Planting, and they're going to have us do a tour of their headquarters and talk about their radical agronomics system, which includes their in-a-box soil testing system. So I've been there. It's going to be really cool. I just want to encourage everyone to take a look at that opportunity. Additionally, I do want to remind you that there are CEUs available for today's webinar, and you can use the QR code to self-report those, or you can send me an email and I'll report them for you. And with that, I'd love to open it up for questions. And I know we've already had some good conversation in the chat. So I'm just going to start at the top. Tom mentioned IPNI assumed that Bray P1 was equivalent to Mehlich 3 colorimetric. I will just say that that's a common assumption amongst our labs too. I'm not sure if I think Tom was maybe just making a suggestion or a comment there. I don't know if there was anything else.
Yeah, first of all, thank you, Tom, for sending me those links. Tom help me to with these conversions. And yes, we consider when Mehlich 3 colorimetric was the same as Bray, but we convert to all those data to Mehlich 3 ICP. That is the way that we have in the papers that are more recent. And so all this data that I present were converted to Mehlich 3 ICP.
But I do think that that's a great resource for our labs because we do have a lot of labs that test in Mehlich 3 ICP, but report in Bray P1 or Mehlich 3 color, which are Bray P1, Mehlich 3 color, and Mehlich 3 ICP are not the same value. And it's hard to do a prediction. So having that IPNI standard is really valuable.
Okay.
So Tom also commented, it is fascinating and in my experience commonly seen that drawdown rate is proportional to initial soil test level. It raises the question, where does P go? Is it precipitated, absorbed? Does leaching increase at high soil test levels? Are there studies that report measures of total soil phosphorus or other soil P fractions at the same time as an indicator of fate? And then additionally, is it likely that the declining drawdown rate over time is also related to smaller phosphorus removals by progressively more P-limited crops?
Well,
there's a lot there.
Yeah. Those are great questions, and I have the same questions actually. But the way that I see, for example, for the first two groups that I consider, I called the low and medium phosphorus. In those ones, because we don't have a lot of phosphorus in the soil, my hunch is that we still have some limitation. We are not in the highest yield because probably we are above the soil test, the critical soil test value. And so when you compare the first two curves of the second two, we don't have phosphorus limitation. And so in the first two have less exports because we still are not using the full potential of our crops. That would be my first thing. When you look at the last two curves that we start with high or very high phosphorus, we don't have phosphorus limitation, but it doesn't mean that the crops will grow more. They are in the plateau when we think about a response curve, and you are seeing a huge decrease in the phosphorus in those ones. And what I think in those soils, we have many things occurring at the same time. We have the plants at the full capacity, exporting as much as they can, but they are limited by the yield, the yield potential. I think that we have precipitation. We have, because we have more phosphorus accumulated, we have transformation of some of these phosphorus in less available forms. Because we have a lot of phosphorus, and we may have, of course, depending on the amount, also some transfer of phosphorus to the environment. And so in the papers that we were able to gather for this study, unfortunately, we don't have this information about less available forms of phosphorus. I didn't see papers that we are working at the same time with drawdown and the measurement of forms of phosphorus. We have some, but not enough. We have some data, but not enough to do a meta-analysis. Just one or two papers that are dealing with that. And so this is something that really we need to answer in the future. And yeah, it's really a question that I cannot answer. But I think that we have all those things at the same time. We have crop export, but we have transformation of phosphorus in less available forms at the same time, especially.
Awesome. So yeah, and I think we can all agree that that's maybe an important question to answer next, right? Especially when we start talking about nutrient loss reduction issues or reduction strategy issues, which are really common in the Midwest. Understanding, is the P drawdown mean that phosphorus is leaving our soils and loading into the environment, or is it just coming into a more stable form in the soil that's just not represented in the extraction? That's, I think, really important. And
yeah,
I'd love to know that in more detail for sure. Hydrologic P, or so Zach asked, hydrologic P losses are also proportional to the amount of soil P present. Was it possible to control this factor between different studies? That seems hard, but I'd love to hear your comment on that.
Yeah, well, it's exactly the way that we comment. If you have more phosphorus and Zach works of with environmental phosphorus, and so it agrees with my previous comment. If we have more phosphorus in the soil, we have more transfer of phosphorus, and yeah, that's a tough question. How to the big thing is that unfortunately these long-term studies are so hard to conduct, and we have so many problems with these long-term trials that over the time we just drop them, that we don't have enough data for that. And it's something that we discussed actually in our last 017 meeting, is trying to do an effort and create a group that would put some of these long-term studies for studying drawdown. And we are working on that. If you are interested, any of you that are in this call, if you are interested in talk about that, we are trying to set some not rules, but the way and the minimum data set that we would collect from this type of study for and so in the future, maybe in 10 years, we can have a bunch of studies that we have measuring different things that are important, and so we can come up with answers for these questions. But remember, we'll need many years because it's drawdown study, probably at least 10 years to have a consistent data set.
So I'm going to skip down because Joshua made a really great comment. Perhaps future studies can report crop P uptake as a rough way of separating out hydrologic P losses versus P transformations. Did you look at, I know you didn't present phosphorus uptake in the crop or phosphorus removal through the crop, but is that something you thought about, or you thought about
Yeah.
any?
Yeah. I think this is a very important thing. The thing is that those papers did not present, most of them were not even presenting the crop yield, and so we were not able to get that data and put in our as a factor in our study. And this is for me is the most important one. How much phosphorus we are removing with our crops. This will be the prime information that we needed.
Okay, and then one last question from Zach. Based on your review, what regions, soil types, or ag systems need more data on drawdown? Where are the major?
All of them. It's 14 papers. It's 56 treatments. We need much more than that for a good meta-analysis. I would like to see a meta-analysis with 200 pair of for comparison. We have only 56.
So I don't see other questions. I luckily have written down a few questions that I want to ask. So I'm going to selfishly go into those while maybe some other people put stuff in the chat. One thing I love to ask our presenters when they talk about phosphorus is if they can, I know you use the term legacy phosphorus, but I'd love to hear you define what legacy phosphorus is.
Well, Andrew is this call. You need to ask Andrew about that.
No, I know what Andrew defines it as. I want to know what Luke defines it.
My own view about the legacy phosphorus, the way that I use it is more like a residual phosphorus. When we have phosphorus, when we are below the critical soil test value, I don't think that is legacy phosphorus. That is just the phosphorus that we need to have in the soil for the plants. I consider legacy phosphorus, in my view, when we have phosphorus above the critical soil test value for crops. And so this is when I'm adding more than we need for our crops. But this is an agronomical view of legacy phosphorus. I'm not considering the environmental view of that.
And I'll just note that Andrew has put his opinion in the chat for those people who are interested. But for those that aren't kind of aware of this, the legacy phosphorus can be kind of an interesting discussion in and of itself. So one of my other questions, so I know you discussed that you kind of cut off the tail end.
Yeah.
But when I'm thinking about your phosphorus drawdown, I think about that sometimes, a lot of times I think about carbon buildup. And so there's kind of this inverse relationship happening there in a way. And when we think about carbon accumulation in soil, we know that there can be peaks, and there's a lot of things that control that peak. I'm just wondering on phosphorus drawdown, it seemed like there's a bottom out where it's just not going to draw past that. Yeah. I know you didn't really analyze that in the study, but can you comment on where is that drop off? What's controlling that?
Yeah, I think that's a very interesting thing. And we have here in North Carolina some long-term trials, soil fertility long-term trials, that we have in our control treatment that we have more than 50 years without phosphorus in that one. It's not a drawdown study. This is just the control treatment. But we are cropping that soil, and you cannot see the phosphorus decrease below a certain level. And what I think that is occurring when we have this very low phosphorus, when we reach the bottom, I think the plant is just having other mechanisms. Maybe less available phosphorus is buffering a little bit of this phosphorus. The plant is maybe getting phosphorus from association of microorganisms, or the plant is struggling and trying to get phosphorus from other layers. Something is going on that we cannot, at certain point, reduce more the phosphorus in the soil, but the plant is still there. Of course, it's not growing very well. We have a deficient system, but I think that we have mechanisms, and especially these less available phosphorus forms, that are feeding the system. And so, well, Another thing that maybe the method cannot see that, just our methods to look at the available phosphorus are not good enough to see these differences in the tail of our curve. But you know, as you said, we just wanted to play safe because the difference was so small. We just removed those. But that when I think about different forms of phosphorus, different pools of phosphorus in the soil, that is the part of a drawdown study that will be very interesting to see if you have these other less available phosphorus forms or some other mechanisms that plants are using to survive in that environment. That's a very nice thing to work with.
Okay, so my last question is you referenced that in the study you moved everything to a Mehlich 3 ICP equivalent. I know it wasn't the point of the study, but you've obviously dug into this. Do you have any thoughts on what is the best agronomic soil test for phosphorus? And we can limit it to North Carolina or the Midwest. What, in your opinion, where should labs be driving that conversation? Should we all be doing a Mehlich 3 ICP phosphorus and
this question is even worse than defining legacy P. You know, we have those big things that we need to think when we think about the select different methods. For example, if you are in alkaline soils, high pH soils, we know that we need to move to Olsen because they work in that way, and we don't have overestimation of calcium phosphate forms. When you are in the soils that we have an average pH or in the acid side of soils, Bray, Mehlich will work very well. And so I think for me, what matters is more if you are in an alkaline region or a high pH region, or if you are in a middle or acid soils region. And so we have options. I don't think that Mehlich 3 or Bray, they are different in terms of the capability of estimate a good quality of estimation of available phosphorus. I think when I think about the in the lab side of things, Mehlich 3 is easier because it's a multi-element, but I think both of them are very good. I don't have a preference in terms of thinking about quality of phosphorus estimation.
That was a great non-answer answer. I appreciate
Yeah.
All right, so I'm not seeing any other questions, so I appreciate those of you that were able to hang on there for a little bit. I'll remind you that you can get CEUs for this presentation, and we will share the webinar link hopefully later today. With that, thank you very much, and I invite people to drop off.